Hi everyone, my name is Wenbo. Today I'm going to talk to you about Kyrix-J, which is a collaboration between MIT, Tufts University, and University of Washington. We're actually the same team who built Kyrix, the system that was initially presented in CIDR 3 years ago. And it was a details on demand system, which you can think of as Google Maps basically, but for arbitrary types of data. It can scale to billions of data points by utilizing database spatial indexes and offers a declarative language for rapid authoring. So these are the example applications that can be built with Kyrix, including a basketball data visualization, a map of animals in the rainforest, and a hierarchical visualization of code packages. We later started building extension systems on top of the base Kyrix system. Kyrix-S is for scalable scatterplot visualizations, which was published in VIS 2020. Kyrix-J is for data discovery in data lakes, which is the topic of this talk. So let me first talk a little bit about what motivated us to build Kyrix-J. A data lake generally means the centralized repository of an organization's data. They're hard to understand because there are usually tons of data that come from different sources, are in different formats, and are on different storage systems. More importantly, there are a lot of connections between datasets in a data lake, which is what we focus on here. For example, there can be primary key and foreign key relationships between relational tables, or similar columns between CSV files. There can also be rich connections between non-tabular datasets. For example, video frames can have the same object. So in that sense, those two videos are connected as well. As another example, two pieces of text might mention the same book. So all these types of connections are useful information in a variety of application scenarios. The question we want to ask here is how can we let the user discover and navigate those connections easily? So we looked at existing data discovery systems, including Goods from Google, Amazon from Lyft, DataHub from LinkedIn, and Aurum from academia. We found that they don't support data connections very well. The focus is usually on metadata discovery instead of content-level connection discovery. And it often involves multiple keystrokes, clicks, or lines of code to go from one data set to a connected one. So we figured we need better ways to help users discover and navigate data connections. And that's why we built Kyrix-J. And let me demonstrate first a usage scenario. So here, a user first starts with a text search, finding something related to China. The results show a couple tables in a data lake, from which the user chooses the country table. Now she sees a visualization of countries and their population. The user clicks on China and sees a popover showing a list of tables and visualizations she can jump to. Under table province, the user chooses to jump to the provinces in China and their area. Before jumping, she gets to preview the new queries and the new filters corresponding to the selection. So now at this new visualization, the user wants to see something about the Sichuan province. So she clicks on the circle representing Sichuan and goes to the population of Sichuan over time. So far, the user has completed 2 jumps and wants to go back to the first visualization. So she opens up the history panel and clicks on the very first visualization. And from the first visualization, she can complete another jump to see something about the United States. So this is how Kyrix-J works from the user's perspective. We see data connections as first-class citizens and use visualizations to enable visual data discovery. We have default visualization for each dataset or table, so you can get an app running without coding. Jumps between visualizations are auto-generated based on data connections, and it requires just 2 clicks to perform 1 jump. Kyrix-J also offers a UI for a variety of data discovery tasks, which I'll talk about later. Here's the system architecture. As input, we have a data lake and a set of visualization specifications which are optional. The viz specifications are sent to a viz authoring engine, which generates visualization metadata. And a connection profiler is responsible for extracting data connections offline. Both pieces of data information are fed to an app generator, which automatically constructs jumps between visualizations. The Kyrix-J UI then renders the visualizations and jumps at runtime. Now let's take a look at the connection profiler. We use a simple data model where datasets are tables with columns and data connections are between columns. We treat this connection profiler module as a black box that can be implemented differently, which can possibly handle the transformation from non-tabular datasets to tabular format and identify any kind of data connections. By default, we use the ORM system, which can find column connections based on content similarity. For any custom implementation, it needs to be scalable. That means an ON squared complexity is probably not desirable. The visualization authoring engine compiles the visualization specifications and builds necessary indexes. Each table has a default visualization, which is a word cloud of its primary key column. This means the cold start is instant. We also offer a declarative language for custom visualizations, which supports pie charts, bar charts, circle packs, tree maps, and scatter plots. It is a JSON-based language for now, but in the future, it makes sense to integrate with established languages such as Vega Lite and enable viz authoring directly in the UI. Now let's take a look at the auto jump problem. The input is a set of visualizations for some tables and their connections. The output is a set of jumps, each identified by a pair of visualizations and a filter. Let's see an example jump from a data perspective. Here, we first start at a pie chart showing continents and their area. Then we click on the pie, representing South America, and jumps to a bar chart showing the areas of South American countries. This pie chart is based on the table continent, while the bar chart is based on the table country. The result of this jump is a filter on the continent column of the country table, which selects only countries in South America. Now, from a high level, this filter generation process is actually matching up two columns: the continent column from the country table and the name column from the continent table. Essentially, if we identify the column from the first visualization that uniquely identifies each object, and then match up with some column in the jump 2 visualization, we will be able to construct a meaningful jump. These matching columns can actually be found by the connection profiler I mentioned earlier, which is the basis of our solution. More specifically, we identify jumps for all distinct pairs of visualizations. So for each pair, V1 and V2, we first identify the key of V1, which uniquely determines the objects in V1. Next, we use T2 to denote the underlying table for V2. M is the set of columns that match K1, which is the key of V1, in T2. We can then loop over all matching columns and construct a jump with a filter that joins this matching column and the key of V1. We apply this algorithm on a public dataset called Mondio with 40 tables and 70 visualizations. This algorithm identified over 1,000 jumps between the visualizations. Without this automatic algorithm, it will be very cumbersome for a user to explore this many jumps. Now let's take a look at the Kyrix-J UI. The Kyrix-J UI uses multiple coordinate views to present the jumps in a way that reduces user disorientation between the jumps. First, we allow user to identify a starting table using keyword search. And this simplified ER diagram renders tables as nodes and column connections as edges. There's an icon in the middle, signals where the user is. The visualization view is where the user can see the data and perform a jump. These views present information that is useful for understanding the current query, filters, and visualization. We allow the user to see previously bookmarked or visited visualization in this history panel or bookmark panel to recall history and share them with others. We conducted a user study to evaluate the usability of this interface. We used a Mondio application mentioned earlier with 40 tables, 70 visualizations, and over 1,000 jumps between visualizations. We recruited 8 participants for a first-use study, in which we asked them to perform simple search tasks, such as checking if an island is in the 3rd largest lake in the world. We had a few findings. First, all participants were able to complete the tasks in a fast manner, and the completions were nearly perfect. Second, participants reported that they were able to stay oriented and use the UI elements to keep track of where they were in the data space. Many positive feedback were given as well. For example, people really liked that it was easy to perform jumps to see connected data, and mentioned some particular UI elements such as the search functionality and the ER diagram that were very helpful. People also made suggestions on how to improve the UI. For example, many thought that enabling the editing of filters, queries, and the visualizations directly in the UI will be very helpful. There are also other feedback on minor UI issues, which we have digested and will be included in a future iteration of the system. So here are some closing thoughts on limitations. The assumption that datasets can be modeled as tables might not always be practical. For non-tabular datasets, we might need a customized connection profiler and UI. For example, the nodes in the ER diagram can instead represent videos, and the connections between the videos might represent a list of frame pairs that had the same object in common. Other challenges in deploying the data lakes in the wild include auto-generated table and column names, which will make the jump options less readable. And when there are too many jumps, it can be hard for user to choose where to jump to. We plan to address these challenges in a future release. And that's all. Thank you.